Okay, so this video will explore the first shift theorem. There are three shift theorems, or three theorems rather, with Laplace, and this is going to explore the first one. Now that we've covered all the transforms, so we've done things like the linear ones, f of t equals a, the trigonometric ones, sine at, cos at, the hyperbolic trigonometric ones, so there's cosh and sine. We've done the exponential, both positive exponential and negative exponential, e to the at, e to the minus at, and we've also done t to the n as well. So now that we've got the transforms, there's these theorems. So let's dive into the first one, which is actually really simple. So okay, so if we say that, first of all, going back to basics, we know that the Laplace transform of f of t, equals the integral evaluated at the positive infinity and 0 points of the function times e to the minus st dt. Yeah. So if we want to ask the question, well, what would the Laplace transform be of f of t times e to the minus at? Well, let's just make the substitution. That should be f of t in this case is going to be f of t, e to the minus at, e to the minus st dt. Yeah, I'm just replacing f of t here with everything inside these brackets. Yeah, so it's f of t e to the minus at, if we want to know what the Laplace transform of f of t e to the minus at is. So let's simplify this. Let's check if you can see that. Scroll down a little bit. So that would just work out to be f of t e to the minus t s plus a dt. Yeah. Now that looks quite familiar to something that we know, because we know that the Laplace transform of f of t, going back up, is this thing over here. Yeah, the integral of f of t e to the minus st dt. Well, that is very similar to what we have here. F of t e to the minus st, because that minus t times s is minus st. Yeah, but the what's contained in the s kind of bracket over here, yeah, is just replaced with s plus a. If you can see that, what we're doing, we're saying that we're making a substitution to s plus a. And then we'll end up with what we have over here, which means that if we say that the Laplace transform of f of t equals f of s, capital F of s, just as an abbreviation, then we can say that the Laplace transform of e to the minus at f of t equals f of s plus a. And that is the first shift theorem. So, so that's really all there is to it, to the first shift theorem. So stated more formally, that would just be like this. So we'd say the first shift theorem would state that if the Laplace transform of f of t equals f of s, yeah, just as an abbreviation, that's normally how we abbreviate the Laplace transform of a function. Say, Laplace of f of t equals f of s. Then we would say that the Laplace transform of f of t times e to the minus at would then equal f of s plus a. And that's all there is to it. So let's have a look at a couple of questions just to see that in practice. So let's scroll up. So you can see that. Yeah. Okay. So let's have a look at, say, the Laplace transform of e to the minus 3t sine 2t. So the first thing to note is the simple thing. What do we know? We'll assume that f of t is sine 2t here. So we can say that the Laplace transform of sine 2t equals, well, we know what that is, that's going to be a in that case is 2, on s squared plus a squared. 2 squared is 4. Yeah? And we also know that the Laplace transform of e to the minus at f of t equals f of s plus a if the Laplace transform of f of t equals f of s. Well, here we have the first shift theorem, because the function is being multiplied by e to the minus 3t. So we can therefore say that the Laplace transform of e to the minus 3t sine 2t is going to equal 2 over s. Well, s is now going to be s plus a, isn't it? So it's going to be s plus a. A in this case is 3. Yeah? Squared plus 4. Can you see what I've done here? We've got the 1p3 again. Since the shift is e to the minus 3t, so we know that a equals 3, so we just replace wherever the s is in the normal transform of f of t with s plus a, or in this case s plus 3. Yeah? So we can continue that. We can say it's going to be 2 on s squared plus 9 plus 6s plus 4 equals 2 on s squared plus 6s plus 13. Okay, let's have a look at another example. Let's have a look at the Laplace transform of, say, e to the minus 2t cosh 3t. So again, we've got this first shift theorem going on here. A good approach, I think, I mean, for me anyway, at least, when I'm often doing anything in Laplace, just you get a feel for it when you do a few more questions. Just kind of break it down. So we've got something a little bit scary here because we've got like a product of functions. But let's do what's easy first. So we know what the Laplace transform of cosh 3t is. Laplace transform of cosh 3t. And there really aren't that many questions you can get about Laplace because there's only going to be 3 different theorems and say 8 different transforms. So once you know you get a feel for what the transforms are, that becomes quite straightforward. And then the theorems are just what you do in addition to those things. So we know that there's going to be some kind of shift going on. So let's work out what the transform, the Laplace transform of the function is first. So the Laplace transform of cosh 3t is going to be s on s squared minus a squared. In this case, it's going to be 3 squared, which is 9. So therefore, we can say that the Laplace transform of e to the minus 2t cosh 3t is going to be some kind of shift, the shift theorem. So always write down the theorem that you're going to use. I find that helps me quite a lot. So we can say that the Laplace transform of f of t equals f of s, or if, rather, the Laplace transform of f of t equals f of s, then we can say that the Laplace transform of e to the minus at f of t equals f of s plus a. So we've got here the normal transform, f of s, which in this case is going to be s on, whoops, did that wrong, it's going to come down over here. It's going to be exactly the same thing, just wherever we had the normal s, like over here, we're going to replace the s with s plus a. So it's actually very straightforward. So we've got an s over here, so we're going to replace that s with s plus a, and the a here is referring to the a in the e to the minus at bit, which over here is referring to the 2. Yeah, so it's going to be s, in this case now is going to be s plus 2, yeah, all over s plus 2 squared minus 9. And that's really all there is to it. It's really as simple as that for first shift theorem. So let's carry on with that. So that's going to be s plus 2 on s squared plus 4 plus 4s, yeah, minus 9 equals s plus 2 on s squared plus 4s for minus 5, yeah. I think that's correct. Okay, so let's do another one. Okay, so let's have a look at, can we see that all right? Yeah, okay, let's have a look at the Laplace transform of 2e to the 3t sine 3t. Okay, so let's exploit the property of linearity to begin with. So we can say that that's going to be equal to 2 times the Laplace transform of e to the 3t sine 3t. Yeah. And we know that the Laplace transform of sine 3t equals 3 on s squared plus 3 squared, which is 9. And now we've got the property of shift going on. So again, I always like to write down the property first. The Laplace transform of e to the minus at f of t equals f of s plus a. Again, obviously providing that the Laplace transform of f of t equals f of s. So all we do is just replace wherever s was with s plus a. So we can say that therefore the Laplace transform of e to the 3t sine 3t is going to equal 3 on s. Well, s is now s plus a, and a here is going to be 3. Yeah. Not the 3 in the argument of the sine function, okay? It's the different 3. It's referring to this 3 over here. It's actually, sorry, it's going to be s minus 3, isn't it? Not s plus 3, because the definition of the first shift theorem is that for s plus a, the e to the index has to be a negative a, yeah? And since here it's positive, so we know that this is going to be negative, so it's actually going to be s minus 3 squared plus 9, which equals 3 on s squared plus 9 minus 6s plus 9. And that's going to equal 3 on s squared minus 6s plus 18. Therefore, 2 times the Laplace transform of what we said before is then going to be 6 on s squared minus 6s, so actually plus 18, plus 18. Okay. Okay, let's have a look at another one where we're trying to find the Laplace transform of 4t e to the minus t. So let's first of all exploit the property of linearity. 4 times the Laplace transform of t e to the minus t. So first things first, we know that the Laplace transform of t to the power of 1 equals, well, we know that the Laplace transform of t to the n equals n factorial on s to the n plus 1. So here we've got 1 factorial on s to the power of 1 plus 1, which is 2. So we know that the Laplace transform of t to the 1 is 1 on s squared, first step. Second step is that we've got a first shift theorem going on here, e to the minus t. Again, let's write it out. Laplace of e to the minus at f of t equals f of s plus a if the Laplace transform of f of t equals f of s. So we can then say that this whole answer is going to be 4 times 1 on s squared. Well, s is going to be 1, isn't it, here? Because e to the minus at, a in this case is 1. So it's going to be 1 on s plus 1 squared. Yeah. Which equals 4 on s squared plus 1 plus 2s. Simplify that. 4 on s plus 1 squared. We could say that as well. Yeah. Okay, let's do another one. Let's do, let's do the Laplace transform of e to the 3t sine 2t. Okay, so first things first, we can say that the Laplace transform of sine 2t equals 2 on s squared minus 2 squared, 4. And the shift theorem would state then that e to the 3t, shine 2t. You start to see a pattern here now. There's just going to be 2 on, well, we're replacing s with s plus a. In this case, it's going to be s minus 3. And the reason it's going to be minus 3 is because the shift theorem states e to the minus at f of t equals f of s plus a. Yeah. So e to the positive at is going to be f of s minus a, and a here is 3. Yeah. Or minus 3 really. So it's going to be s minus 3 squared minus 4. That's going to be 2 on s squared plus 9 minus 6s minus, minus 4. So that's going to be equal to 2 on s squared minus 6s, 9 minus 4, that's going to be 5, yeah? Okay, let's do one more. So let's say the Laplace transform of t to the 3, e to the minus 4t. Okay, so first things first, Laplace of t to the 3 is going to equal, again, let's write out Laplace of t to the n, we know, is a standard transform. It's going to be n factorial on s to the n plus 1. So that's going to be 3 factorial on s to the 3 plus 1 equals 6 on s to the 4. Yeah? Therefore, the Laplace transform of t to the 3 e to the minus 4t should be 6 on s plus 4 to the power of 4. Yeah, and it's as simple as that.